Today, we are going to discuss about two-dimensional arrays in C. We shall see why two-dimensional arrays are required, how memory is allocated for two-dimensional arrays, and how two-dimensional arrays can be processed using a program. So this is the topic for today, two-dimensional arrays in C. First, we can see why we need to have two-dimensional arrays in a C program. Many programming problems require to maintain a table of elements of the same data type. For example, programs to maintain and process matrices. If you want to see a concrete example, consider a program to compute the grades obtained by the students in the continuous internal evaluation, where you may be having 4 columns like the marks obtained for assignment, marks obtained for attendance, marks obtained for the internal examination, and the total marks. Here every cell is going to be a numeric field, and maybe the column headings represents the assessment 1, 2, 3, 4, and each row represents a student. So that is a concrete example if you want to think about it. And C provides what are called two-dimensional arrays to store a table of values like a matrix. And programs in the domain like machine learning require to use n-dimensional arrays. And in C, it allows you to create an n-dimensional array for a given natural number n. Our agenda today is to discuss about two-dimensional array in C. We can try to understand what is a two-dimensional array by considering an example. Here, it shows a two-dimensional array, namely T, which can store 20 elements in 4 rows and 5 columns. So it's actually a 4 by 5 two-dimensional array or matrix. And the elements can be accessed by indexing the array. So you have both the row index varying from 0 to 3 and column index varying from 0 to 4. So what we show is that if there are m rows in the matrix and n columns, then the row index is drawn from the interval 0 to m minus 1. 0 to m minus 1. Here there are 4 rows, so 0 to 3. And the column index are drawn from this interval from 0 to n minus 1. Here n is 5 number of columns. And ijth element of the table T or the matrix T can be referred by Tij for all the values of I in this interval and for all the values of j in this interval. So if you want to just look at the indices to access a two-dimensional array, it looks like this. So this cell of the array can be accessed by using the index values 0 and 0. If you always use I for the row index and j for the column index, then I equal to 0, j equal to 0 for this particular cell. So this is what I am trying to tell you. Here I am representing row index in red color and column index in blue color. So every cell can be indexed using the row index and the column index. And you can see that you can find a relationship between the index values. For example, if you look at the principal diagonal of a square matrix like this, I is equal to j is the condition which identifies that that particular cell is on the diagonal. Or you can see that for all the cells below this principal diagonal, the row index is greater than the column index. On the diagonal, it is equal, and above the diagonal, it is less. The row index is less than the column index. So this kind of relationships you can observe and use for solving problems like checking whether a matrix is diagonal, a matrix is upper triangular, like that. Now, let us look at memory allocation for a two-dimensional array. Suppose you have a function like foo in which you are declaring a matrix or a two-dimensional array with 2 rows and 3 columns. Each element is of the type integer. So you will be getting memory allocated like this. So what's it? Creation of an instance of this function foo. More about instance creation will be discussed when we discuss about user-defined functions. Now, when a function is created, memory needs to be allocated for all the variables declared inside, and here you are declaring a two-dimensional array or a table with 2 rows and 3 columns. So here you are demanding to allocate a sequence of 6 consecutive memory locations. Each one is 2 bytes, because assuming that 2 bytes is the requirement for an integer. So it's just like a single dimensional array with the 6 elements. Okay? And here is how you can access it. In the case of a single dimensional array, only 1 index. In the case of a two-dimensional array, 2 index, the row index and column index. So if you look at, you can see that memory is allocated as if it is like a single dimensional array of 2 into 3, 6 elements. The first row is stored first, the first row, elements at row 0, okay, followed by elements at row 1. And this is what is called the row major representation of a matrix, where the elements of the first row is stored before the elements of the second row. And even though memory is sequential, it's just like a sequence of bytes, regardless of whether it is a two-dimensional array or even a three-dimensional array, the memory is sequential. And in the program, you can access it like a matrix. That's the difference. So you can view it as like this. So, but now that the memory is sequential, right? But you can depict your two-dimensional array as this. And array name, just like a single dimensional array, here the array name is T, which is actually the starting address of the sequence of locations allocated to the array. In this particular case, 500. Now, we saw that it gets memory allocated as if it's a one-dimensional array of 2 into 3 integers. And it can be viewed as, in fact, 2 one-dimensional arrays, T0 and T1. If you want to remember why the index is I and J, it's like for row 0, you have I value fixed as 0 and J values varies from 0 to 2. So you can view the first row as a single dimensional array. Similarly, the second row. Now, we can look at the syntax for array declaration. It's very simple. What's it? First is the data type of the elements of the array. It was an integer for the previous example, followed by the array name. It was T in the previous example. Then the within square bracket the number of rows. In the previous case it was 2, and then the number of columns in square bracket. In the previous case it was 3, and in general the size 1 or size 2 can be a positive integer constant or a constant expression resulting in a positive integer. Example, it can be a positive integer constant like this, or it could be a constant expression like this resulting in an integer. So you can find why you need this kind of a syntax. Maybe it makes it meaningful, or it makes the program more readable. Maybe in that array you are having, say, 150 rows, but 150 is constituted by 50 people. Each one is having maybe 3 different values, like that. It depends. You are free to go for like this or like this, or it could be a symbolically defined constant like has defined size 100. Then you can use size 1 here, same as saying 100. We have seen the advantages of using this kind of symbolic definition when we discussed about single dimensional arrays. Yeah. Now we are going to look at the syntax for accessing. Now we just have looked at syntax for declaration. Now the syntax for access is this. The array name. In the previous example it was T followed by the row and column index. You know that the row index I ranges from 0 to size 1 minus 1. That is the number of rows minus 1, and J index varies from 0 to number of columns minus 1. Now we can see how can you access the cells in an array, two-dimensional array, in a systematic order. Suppose you have a two-dimensional array like this. So there are 4 rows and 5 columns. Now we want to see how can we systematically process the elements of this array. So I'm going to, you may go it like first column, then second column like that. But what I'm going to tell you is about how can you process it in row wise. First, I will start from the first row, first cell. Okay. Then I will move on to the second element in the first row, then the third element, then the fourth element, and going to the last element. So what I did is, I fixed the row as number 0, and the column index J is ranging from 0 to 4. That's what I did. So after that, what should I do? I have to move to the second row. So initially, the row index was fixed at 0, and then J varied from 0 to 4. J less than 4 means until J becomes 4. And J less than 5 means. What is 5 here? 5 is the number of columns of this matrix. Okay, I did this. So what should I do now? Just reset I to 1 and then do the same. So I am processing the next row. Then I have to increment I to 2 and then execute the for statement to access the elements. And how will you access it? That you can decide depending on what requirement you have. Then I is getting to 3 and I am processing the last row. So if you recall, what we did is J is ranging from 0 to 4, that is the number of column minus 1, for every value of I from 0 to 3, where 3 is the number of rows minus 1. That is, you can do it like this. So the outer for loop, in the outer for loop, the loop control variable is the row index, and in the inner loop, the loop control variable is the column index. If you do this, then it is row major processing. You are processing the first row, then the second row, like that. And in general, we can say that for a two-dimensional array, you can have a nested for loop like this to access it. And in general, this is the number of rows. If it is an m by n matrix, this should be m, and this should be n, where m is the number of rows and n is the number of columns. So I think you're getting how you can process the elements of a two-dimensional array in a systematic order. So you can fix it. It's a very easy to remember syntax. It's a nested for loop. And how will you access it depends on what is your requirement. Maybe now we can use that card to read elements into a two-dimensional array. Suppose you have a two-dimensional array with 4 rows and 3 columns. How will you read it? Like this. So this is fixed, and now the processing is reading elements one by one to each of the cells. And if you execute it, you will get this message displayed. And suppose the user is giving this as the 4 by 3 matrix. Then after executing this code, you will get the array filled with these values in that order. Okay, the first row is read first, and then the second row, because we formulated the loop in the row major order. Okay, that's it. Now we can see how can you display. It's very easy. Suppose you have a matrix like this. How will you display? Here the processing will be printed out. Each element you are printing. And if this is the matrix, so you will get it printed like this. And not that initially after this I am printing a /n. That means I am going to the next line. And after printing a row, I am coming back to the next row, and just before the next row I am leaving a /n. That is why I am getting it printed in the next line. So how to format it, you can decide. How many space you need in between. Whether you want to go to the next line, maybe you can display in a single line if you want. Maybe you put a semicolon, likewise. But this would be the more natural way to print a matrix. And anyway, if you process this, the matrix is not getting changed because you are not modifying it. Now maybe we can also look at how can you modify it. Just a simple example. Suppose you have a matrix like this, and you have given with this code. Can you see what this code is trying to do? So this is the processing. This for loop is already fixed. This is how you systematically process each element. So what I'm doing is, to each element, I'm adding 10 to the existing value. So if you process it, every position 10 is getting added. 10 becomes 20, 11 becomes 21, 12 becomes 22. Likewise, everywhere you are adding 10. Okay, this is just an example. You can decide what you want to do. So today, we have looked at two-dimensional arrays. They are used to store matrices. And we also have seen how memory is allocated. It's allocated as if it is a single dimensional array of m into n number of elements. But you can access it like a matrix by using the row index and column index. And the row index varies from 0 to m minus 1, where m is the number of rows. And the column index varies from 0 to n minus 1 if n is the number of columns. Also, we have seen how we can systematically process the elements of a two-dimensional array. So we have formulated a nested for loop, and the processing depends on what kind of a problem that you are solving. In the next class, we can see some concrete operations on two-dimensional arrays. Thank you.